Hi everyone, welcome to my channel and welcome to this video. So in my past few videos I have talked about multiple ways to upgrade a running process or a running software on basically a running server program on a server machine, right? And we discussed about various ways on how to upgrade a process on a given remote server. We discussed about SODU port, how another process can how or rather how multiple processes can listen on the same port, using which we can run the upgraded version of our process parallelly on listening to the same port on the machine, and then send a kill signal to the older process, which can then gracefully shut down and drain the connections. That was one process we discussed. The other process we discussed was how we could use systemd socket activation as well, wherein we would separate out the listening socket, give it to systemd, let systemd manage it, and our process purely have the business logic, and it receives the socket from systemd and then starts using that. That way, if the process dies, new connection is stored in the socket buffer, and that gives us some breathing space to restart the process, and then next systemd will take over, and it will, whenever it will see that the process is dead, it will restart the process, right? So these are a few of the methods we discussed, right? But for each and every method we did mention something like the old process or the dying process needs to shut down gracefully, right? It needs to drain the connections before when it receives the kill signal, before it can terminate or it can withdraw itself, right? But one thing that we never really discussed is what do we mean by graceful termination of a process, right? What do we mean by it? Or what do we mean by gracefully terminating a process after it has drained all the connections it has been handling, or the request, or after it has drained all the requests that it has been serving? And that's very important, right? That's one of the core parts of seamless process upgrades or process swaps, where no request data is lost, right? Or in-flight requests are handled properly before the process can be shut down. So in this video we are going to discuss what do we actually mean by gracefully shutting down a process, or handling the request to shut down or terminate the process. And while doing so, first take care of the existing in-flight request, drain those requests, and then shut down, right? So we'll be discussing about graceful termination of process, and we will also see how we can simulate that, or we can do that in practice using C. So yep, without further delay, as always, let's get started. Okay, so in this video I'll keep the example pretty simple. I'll go with a single threaded server application or a socket program which will act as the server. And what I want is, when that process receives a kill signal, or when we want to terminate the process would not die abruptly. It would not die suddenly, but rather before getting terminated, or it would handle any in-flight request. It will drain those requests and it will terminate after that. So that's what I target to do with this in this example, and I want to keep it very simple. So in order to understand what a process typically needs to do before it can terminate, in order to gracefully shut down, is so before going into that, let's have our old server program skeleton to understand it better. So a server socket program, and I have used this skeleton flow several times in my past videos as well. So the first thing that a server socket program would do, or a listening socket program would do, is it would first create or instantiate a socket, create the socket with its desired type. After that, the next thing it would typically do would bind the socket to a particular IP and port. After that, it would set the socket to listen mode. The next typical thing it would do is start accepting connections, right? And typically it would try to do it in the loop, and what it would get for every new connection is basically a client socket FD, right? And then what it would want to do at this point of time, it could fork a worker process, but since our application would be a single threaded one, what it would typically do after getting the client socket is go into a loop and start reading from this client socket. And once it has read something from the client socket, it would process that. This would mean generating a web page or whatever it would want to do, like crunch some numbers or whatever. And once it has processed, what it would do is it would write it back to the client socket, or to the client socket FD, right? And once it's done with everything, it would want to close the client socket FD, right? And when the server wants to exit, it would close the server socket as well. So this is like a normal flow, right? And if I draw a parallel with a client socket program, or just a client basically. So the first thing that a client would also do after it comes up, basically a client of this socket. But remember, in a typical peer-to-peer connection, no one is actually a server or actually a client, right? These are just two peers talking to each other. Server and client definition is something that we impose on them, right? This client could itself be acting as a server for some other client or some other peer. So it could be accepting connections. Then with that, the data it receives, it could be proxying it or sending it to this server program as a dependency and get the data from this server to back here, and then send it back, do some processing on its own part, and then send it back to its own client, right? So this client can pretty much be acting as a server for some other client. So that's what I'm just trying to say, that it's basically a P2P program. Like it can send, it can receive, it can process, and all those kind of things, right? So the first thing it will also do is it will instantiate the socket, right? And then what it would want to do is it would want to call the connect call, right? It would want to do the connect call. It would want to write, and again this perhaps would happen in a loop, but anyways it would. So the socket it will get from this socket initialization call, it would want to connect to that socket, then it would want to write to that socket, and then it would want to read from it, right? And typically what I would want to do in this server socket program, which would know how to gracefully shut down and handle in-flight requests, is whenever it wants to terminate, the last response it sends, or the response it sends as a part of request drainage or connection drainage, it should contain some keyword from which the client knows that the server is shutting down, right? So that the client can do cleanup on its own part. It can send certain things to its own clients and things like that. So basically I want the client to know in the last drained response that the server is now shutting down, right? Or the server has shut down. I mean, the TCP connection would be doing so using FIN packets already, but I would want to do that at the application layer as well, where the server explicitly sends a marker to the client saying that, hey, I am now shutting down, no more requests I will be entertaining, right? So typically this connect call, so we know that the accept is a blocking call, right? So the connect basically correlates to or comes to this part, the accept part. So the accept blocks the moment a client tries to connect, this accept unblocks and it gets the client socket FD, right? Obviously write would correlate to read, and read would correlate to server's write. Okay, so now how and when can the server get terminated? So how? It's pretty simple. Like it can get like in our local while testing, we will simply send it a SIGINT using Control C, and when deployed on a server, the kernel can send it a SIGINT, or any other program can send it a SIGINT using the kill command. And at what points can that termination happen, right? Before it goes into the accept loop, like, so as I said, accept often happens in a loop, right? At any point here before the accept loop starts, or just when the loop has started, it can receive a kill signal, right? And if that happens, we are fine, right? If it just happens before accept or at any of this stage, the client will never able to connect in the first place. So there is no question of in-flight request or anything like that. So we are good here, right? Let's say it receives a termination request when it's blocking on accept. Then also we are fine. Blocking on accept means it hasn't got anything till now. So if it dies at that point of time, well and fine. Now let's say it has received a client socket, right? It has received a client socket, and now it has entered the read-write loop. This entire thing, this entire read process, right? This always happens in a loop, right? Until and unless the server or the client decides to kill the connection. So let's say it has received the client socket FD, and it has started the loop. It has started, let's say, the while loop, and then it receives the termination request. Then we have a problem, because the termination request could have happened anywhere. I'll just put a big cross here saying that the termination request has happened somewhere here, right? So now if I go inside this loop and go a bit granular, it could have happened just before the read was called, right? it could have happened just after or while it was reading, right? While it was reading or after the read has happened. If it happens after the read call was unblocked, that is again read and write both are blocking call, and I'll make the process as blocking call as well for simplicity. So if the termination request happens after the read call returned, it means the client thinks the request data is being processed by server. If at that point in time the server fails, the data is basically lost, right? The data will go unprocessed, or it won't be a graceful termination. Same if it happens while it was processing it, same if it happens just before it was able to write. Because if it was terminated before it was able to write, it's a wastage, right? The server processed the data but it couldn't send it back to client. It's a loss at the client's part, it's a wastage of resources at the server's part as well. Even after write, if it tries to go down, then also it might happen that the client again has gone back to after reading. It might have again, by that time it comes to the end of the write, the client might have gone to the next cycle, and it might be again trying to write something to the server, right? If again at that point of time the server goes down, it won't be a graceful termination, right? Because the client is waiting to write something to the already existing connection. So this is our most critical part, right? If we get a termination signal here, we should be able to do a graceful termination. We should somehow capture that termination request, process the whatever inflight request, or just do a last round of read and write with the client, send the client the processed data along with the shutdown marker, that it's pretty much the server telling the client that, hey, I'm going down, I won't be able to serve further requests. So that's pretty much all the server wants to do in order to gracefully terminate, right? Now the question is how we can do that. A kill signal can occur at any these points in time. How can we handle that signal, right? So in order to handle this signal, the kill signal or control C, which is again simply the SIGINT signal, we will write something known as the signal handler in C, right? What a signal handler allows you to do is, it's basically a signal handler allows you to associate a routine, a subroutine, basically a C function, with whatever signal you want to handle. So what happens is that whenever that particular signal comes to the program, so in Linux, not all signals are handleable, right? Only a subset of all the signals are handleable by a user level process. And also there is a concept called default disposition of a signal, right? Default disposition of a signal by the kernel. So what happens in this case is that if your user level process receives a signal for which the process has not registered any handler, so basically the process doesn't know what to do when it receives that signal, what the kernel will do is it would trigger the default disposition of that signal, and that would get triggered. So what it means is, for example, the default disposition for the SIGINT signal is to terminate the process, right? So if the kernel sees that the user level process is not taking care of the SIGINT signal that has been sent to the process, the kernel will simply terminate the process immediately, right? Another example could be 6F, SIG, SEGV. So if there is no, it happens when there is a segmentation fall or like a memory violation. So what happens in case of a 6F is that if there is no handler registered by the process, what the kernel will do is it would immediately terminate the process and generate a code dump, right? So default disposition is nothing but a default behavior that the kernel follows when the process has not registered any custom handler for the signal. Okay, so what we pretty much need to do as first part of graceful termination is capture that signal, capture the termination signal. And for this tiny program, I would consider the only kill signal that this process would be getting, or the only signal that we will handle, is SIGINT, because it's easy to demonstrate. I can simply do a control C from my local and I can simulate that. But in real world, you can handle all the signals that you think you need to handle, right? So what we need to do is write a custom handler, right? A custom, basically a function in C, and associate that function with the SIGINT signal, right? And we can easily do it using the sig action call in C, right? The sig action call is a library call in C using which we can associate a handler with the desired signal. And what happens is that whenever a signal is sent to a program, and if there is a registered function for that, it's like a trap. It's like a trap sent by the kernel to the program. And what happens is that the process stops its immediate execution. If it would immediately stop its normal flow of instruction execution, it would go to the memory address where the function is located, which is supposed to handle that signal. It would execute that function, and it would immediately come back to the place in the program which it was executing last, right? So in short, a signal occurs, the the process stops its normal functioning. It goes back to the memory address of the function, executes the function, basically the signal handler function, and it comes back to the place from where it left, right? And it continues with its normal execution. So let's say, for example, if the termination call came here just after the read and after read and before process, so what would happen is at this point the flow of this program will stop. It will go back to the function, like the handler gets executed, and then it will again come back to the exact same point where it left, right? The handler needs to be really quick. Why? Because remember, your normal flow of the process is stopped right now, right? And like your program is actually in a vulnerable state, because if you do too many things in the handler and then when the process returns to its normal execution, there might be consistency issue, right? It's preferred that in the handler you do not execute much of your business logic, rather no business logic, but just set a flag or unset a flag, something like that. And then once it's back to the normal execution, then it can check that flag to decide whether it needs to terminate or whether it needs to do something before proceeding with its normal flow, right? So that's how typically a handler is designed, right? So that's how we can use a handler function to handle kill signals or signals in general in a Linux user level process, right? Now that's the first part. Now we know that we have received a request to get terminated from the kernel. What do we do next? One typical thing that usually processes do or programs do when they are designed is, before going into this client read write loop, every time you check whether the terminate marker is set. If ever the terminate marker is set, what you do, you basically do a one round of read write, right? You do a one round of read, you process that request, the response that you generate, you add your shutdown marker or termination marker there, and you write it back. And after that, you simply close. This way, you are pretty much gracefully telling the client that, hey, this is the last message I'm going to send you. I'm done with the processing, and after this, I'm shutting down. And you do not go back to the normal loop again. So at the beginning of the read write loop, you simply check the marker, drain any inflight request, send it back to the client, and then you make the server die. That's a very straight and simple way to do this graceful termination. There are complicated scenarios as well when it's not single threaded, it's multi-threaded. You know, there are a number of client sockets. You need to somehow shut down you need to drain each and every one of them, and all these complexities come. But the goal of this example is to show to keep it simple and to show how signal handling and graceful termination can be done at a simple basic level, right? So yeah, in our program as well, we are going to follow the marker approach, where we will check the marker, take the decision, terminate or not terminate, and continue. So that's the overall plan and overall working of a graceful termination procedure. And next we will try to implement this thing in a simple C code and see how it works. Okay, so let's jump to code. So I've written here a very simple server program. All it does is it's a simple TCP server socket program. And I'm also, so first I initialize the socket as sock stream. I enable SODU's port. It helps in testing, because whenever I'm killing it, I do not have to wait for the kernel to release the socket. Then I do the bind call and I put it in listening mode. And then I go into the loop. The first is the outer loop, inside which I continuously try to accept a client socket. Once I have accepted a client connection, I pretty much do a log from where did I get the connection. Then I start another loop, and this is basically the read write process loop. So first I read. If I see nothing has been read, I break. It means maybe the client has died or something like that. And then I go to process message. Process message, it does nothing but it simulates some work by sleeping for 5 seconds in a loop. I'll soon let you know why I could have slept for 5 seconds, right? But instead of doing that, I'm sleeping for 1 second each inside a five time loop, right? I'll tell you in a moment why I'm doing that. And then I'm simply creating my response, receipt from server, some strcpy, str concatenate, like string concatenations, and then I'm writing it back, right? And then I'm also logging that it has processed the message. In the client is a simple Python client, and all it does is that in a loop, it initializes the socket, it connects to the server, and then in a while loop, it simply sends a hello message to the server, and then if there is no data, it breaks. And this is the interesting part. So I also look for a server terminating marker in the data, and if that's present, I try to print it, I try to log it. And this is actually the place where it would want to run some cleanup code, right? But I just won't do it right now. But this is when the client knows that the server is terminating. And yeah, that's pretty much it. It's a very simple client. So now if I right now run it, if I do a server .c -o server, let me just divide my screen as well. If I run the server, if I run the Python client, it would say that it has accepted a new connection. And the client is basically it's now, it was processing, and then it received a message. I can simply decode it to remove this B, but that's fine. I'm just printing it as it is. So yeah, after every 5 seconds, it's basically sending a message. The server is sleeping for 5 seconds, simulating some process, and then it's sending back, right? So right now, if I do a command C, it simply dies. The client doesn't get any custom server termination message. It simply dies. The client sees that there is no data, it breaks, right? And yeah. So now we would try to make this server a bit graceful, where it senses that it's going to terminate, drain the request, send the client the marker that it's going to terminate, and then die. So let's do that. So the first things first, we need to set that marker, that the termination marker, which will be set by the signal handler function. So first, let's write a signal handler. So for that, the first thing that I need to do is include something called signal.h header file. Then I would need to declare a flag, basically a boolean flag 01, to know when it has been the process has been marked for termination. So I could have simply done something like int terminate, right? But I cannot. The reason being, it's always preferred that from the signal handler function you do only atomic operations. You don't do any operation, or try not to do any operation that's non-atomic in general. It's not preferred that whatever you do gets broken down into different instructions. If that happens, there can be consistency issue when the normal flow of the program resumes after the signal has been handled. So int assignment in general, or a int update, or a variable update is in general a non-atomic operation, right? The entire word gets broken down into multiple instructions to avoid such consistency issues. So instead of a normal int, what I would want to do is use something called atomic, a sig atomic type. So C makes sure that any update to this variable terminate is actually atomic operation. So we'll use this. Then we'll create a function called mark for termination, and we will get the signal number here. So this is what C expects you. C expects you to have this interface, because you will be providing this function to sig handler's parameter, sig actions parameter in form of a struct. This is a function signature that C prefers to have. Okay, so here I am only checking for sigint. And there is a typo. If signal number is sigint, we'll do terminate equal to 1, and we'll return. So now in the process message, we'll just modify it a bit. We'll check if terminating, actually let's call it terminating, because it's in the process of getting terminated, right? So we'll call it terminating. So if terminating equal to 1, which means it has been marked for termination, we'll create a variable called char termination msg equal to server terminating, and this is the same marker that the client will look out for. Terminating, yeah. Another concat, and rest remains exactly same, right? Basically I appended server terminating marker or keyword at the end of my response that I generated. So now I need to watch out for this set for termination at the beginning of my loop, as we discussed. So here, before doing anything in the outer loop, what I'll do is if terminate printing equal to 1, I'll simply print f terminating. Then I will close the sock fd and exit. So this is a simple case where we have just terminated a connection, or we have just handled one connection, the connection has died, and then we are again going to next round of accept a call. And if we get the termination request before that, we don't care, right? We can simply close the socket and terminate the program. But what's important is this part of code. Now we have already started interacting with the client, right? So now we need to gracefully shut down. We'll say printf terminating, same as before. We'll do close fd, sock fd, but we can't close the client fd, right? Why we can't close the client fd? Because before that we need to drain any in-flight request, right? So for that I won't just directly call process message, but what I'll do is I'll create a new function which is called, because process message already expects that the read has been done, right? Process message will always expect that read has been done and you are getting the message that has been sent by the client, right? But drain and exit will not assume that. Drain and exit will assume that the read has not been called yet, because it's happening it's called directly at the beginning of the loop, right? Just when the client interaction loop is beginning, and it will just straight away do a read, last read from the client, get whatever the client has in flight, process it, send the message to the response to the client with the marker, and die. So we'll call it drain and exit. This socket fd will basically be the client fd, the client socket fd. We'll store it in the buff array. If size less than equal to 0, and simply say could not read probable client close. Close sock fd, right? And then, so now we have read from the client, right? We have read from the client. So proper way to do this would be, just after you have done the last round of read from the client connection for the socket, you would want to make sure that no one else is able to read anything else from this socket. And so for that, the library call that we can use is shutdown, right? And you can pass shut rd. So what this does is that it closes the read end of the socket. What this means is this thread or any other thread cannot read anything else from this client socket or this particular socket file descriptor. So then what we do is we basically process this message, and for that we can simply use the process message function, and it's simply a marker that I'm passing. I'm telling it that it is actually terminating. So I set it as 1. So in this case, the older one, I was passing it as 0, because this is a normal flow, right? It's not terminating flow, but it's a normal flow. So that's why I was passing it as 0. But this time I am passing it as, so actually I could have read it from the global variable as well, but I'm just passing it as a function parameter, which is fine, I believe. And this time so this time when I'm calling it from within join and exit, this is not the normal flow, this is the termination flow. So I'll call it with 1. Now what I'll do is, again, if we want to do it properly, we will again call a shutdown call on the client socket fd, and this time with shut wr. It means this is the last write to this client socket fd has been done, and no one else can, this thread or no other thread or no one else can write again to this particular client socket fd. and after that we simply close it. And that's it. That's our drain and exit function. And all we now need to do is call this function here, right? And we are pretty much done. Oh, and it seems like I have actually forgotten a very important part, perhaps one of the most important parts, that is registering this function as a signal handling function or a signal handler. Basically, we need to register this function as a signal handler for SIGINT signal, right? How do we do that? And that's where the sig action library call comes into picture. So we need to define a struct called sig action. Let's call it SA. We'll mem set it to 0. And we will mark SA handlers. So it's just a process that we need to follow to register this function as a signal handler. And sig action expects this SA struct. So now we will call sig action with the first parameter is the SIGINT, the basically the signal number. Next parameter is SA, the handler struct, and the last one can be null. So these are nothing but macros, and you can see it's defined in signum generic.h, and SIGINT is basically kill-2, right? Okay, so that should be it. Like that should register our signal handler. Okay, I believe I have made one more error over here in process message. So basically, after doing the string concatenation, I need to update the response size as well. Now it should be good, I believe, and let's compile and then let's run it. Now I'll run the client as well. So it's the first message is perhaps getting processed, and we got received from server hello1. So hello1 got sent, it got processed, it got sent back. And now if I do a control C, so see, even after I do the control C, it processed the last message, it marked it, it said terminating. Then it received the last message, which is basically it had the marker, the client had the marker called server terminating, and then the client was able to detect this, and it said exiting client server since server is terminating. So this we print only when we have received the marker. So let's try once again. So there's a normal flow, hello1, hello2. Let's just let it do another one. And what if I do now control C? So depending on when it received the termination signal, it would still process one last hello. In this case, it was maybe it got the signal just after it had received 4, or while it was processing 4, it did a last round of read write, which is processing 5, and with 5 it sent the server terminating message, and after that it terminated. And the client would process this server terminating marker, and it exited, saying that the server is terminating. So whenever this the termination signal will be received, even if it was processing any message at that time, it will, so the server will still try to do a last round of interaction with the client, just making sure it processes anything which is in flight, and then it will send back the reply with the terminating marker. It will terminate, the client can process the terminating marker, and it can do any cleanup. In this case, the client doesn't do any cleanup, it simply dies or it simply terminates, which is fine. But in real world, the client could be sending or processing this server termination message to its downstream clients, or do several other things as the case may be, right? So that's an example of how graceful termination can be handled, or how this can be used while terminating a process, or swapping a process, or upgrading a process during a deployment and things like that. So remember I had mentioned here that we need to do sleep 1 and not a sleep 5 or sleep 10. So this is a special case. So what happens is, if a signal is sent to a process which is sleeping, let's say it's supposed to sleep for 10 seconds, until now it has only slept for 5 seconds, and at the fifth second it receives a signal which breaks the sleep, wakes up the process goes back to the signal handler, handles the signal and comes back. So you might be expecting that it will again go back to sleep from the fifth second and sleep for 5 more seconds, but that's never the case. The sleep is broken for good. So that's why when doing this kind of tests or this kind of experiments with signal handling where sleep is involved, you should not sleep for a big period of time, but you should sleep in chunks, so that if the if the signal comes here at the end of the first sleep or the second sleep, the process gets woken up after the second, but then again it loops back and it sleeps for 3 more seconds, that is 3 4 and the fifth, the third, fourth and the fifth second, right? So that's just the hack that I've applied here. So yeah, I guess that's it for this video. I just wanted to show how we can handle signals in C, how we can register a signal handler for a given signal, how we can use that for doing last round of client interaction for joining request, basically terminating a server gracefully, how we can send a marker message or a shutdown message to the client, or a server shutdown message to the client, so the client can take necessary actions or whatever. Since I discussed so much about process upgrades and process termination in my last videos, I thought that I should also discuss about what actually should be the process of termination when we are upgrading a process, or for anything which when we are sending a kill signal to the process or things like that. So I thought I should do that as well, and hence I wanted to discuss about graceful termination, signal handling, and all these things. That's it for this video, and let me know in the comment section below how you have used signal handling in the past, in C, Python, or whatever language you have used, and why you needed it. Was it for this sort of purpose or any other purpose? So just let me know in the comment below. And yeah, that's it for this video, and hope you all liked it. See you all soon.